Welcome back. We can continue to discuss the Fermat Contest by Waterloo with the final 5 problems, which are 21 to 25. Firstly, we have 21, which is the area of a right angle triangle is 54, and the side lengths are integers. So yeah, you can just test Pythagorean triples until it works, right? So the base times the height are the base times height over 2 is equal to 54, right? Because that's the area formula for a triangle. So that means the base times height is equal to, the base times height, not the height times height, is equal to 108. And now we can basically just test Pythagorean triples, right? And you can notice that the only Pythagorean triple that works is 9, 12, and 15. As 9 times 12 is equal to 108. There are no other Pythagorean triples in which the two smaller, which are the two base lengths, have a product of 108. And C is the highest side length, so that's just a hypotenuse, so the length is just 15. So the answer is 15. So now we can continue by problem 22. We have a system of equations. So let this be equation 1, let this be equation 2, and let this be equation 3. Then we can subtract equation 3 and equation 1 to get 2x plus 2 to the y. They cancel out. So we get 3 to the power of z minus 3 to the power of z minus 1 is equal to 633 minus 2259. That is equal to that's equal to 4,374. And yeah, now you can basically just test powers of 3, and you can see that 6,561 minus 2,187 is equal to that. So z is equal to 8. Notice, if z is any higher, then it wouldn't work, because then 3 to the power of z minus 3 to the power of z minus 1 would have been higher than that number, and vice versa for if z was lower than 8, right? So yeah, so the reason we did equation 3 minus equation 1 is because then 2 of the terms would cancel out. Now we can do equation, now we can plug it into equation 2, right? So 3 to the power of z is 6,561. So 2 to the power of x plus y plus 6,561 is equal to 7,073. So you can move this to this side. So 2 to the power of x plus y is equal to 512, which is equal to 2 to the power of 9. So therefore x plus y is equal to 9. And so that's equation 2. You can also simplify equation 3 to get 2 to the power of x plus 2 to the power of y plus 6,561 is equal to 6,633. You can move this to the other side again, so that gives us 2 to the power of x plus 2 to the power of y is equal to 72. So x plus y is equal to 9. Now you can basically just test powers of 2 to get that it's equal to 64 plus 8 equals 72. So x will be 6 and y will be 3. Or x can be 3 and y will be 6. Same thing, right? That doesn't change the product of x, y, z, which is what we're looking for. And you can check that it does indeed add up to 9. So it satisfies this equation too. So x, y, z is equal to 3 times 6 times 8, which is 144. And we're looking for the rightmost two digits. So the answer is 44. Okay, so for problem 23, it's like it's like the working problem. It's like it's like the classical like two builders like take how long, right? It's just the same like types of equations. So we can like solve 23 right here. So let the big N like spend X minutes to build the anthill, and let the small ant spend Y minutes. So that means every minute 1/24 of the anthill will be built, right? And in 1 minute, the big ant can build 1 over x of the anthill, and the small ant can build 1 over y of the anthill. So every minute, 1 over x plus 1 over y of the anthill will be built. And also, that's just 1/24 of the anthill, because when they work together, they'll build the anthill in 24 minutes. So in 1 minute, they build 1/24. We also know that the big ant can take 14 minutes less than the smaller ant. So x is equal to y minus 14, or x plus 14 is equal to y. So that means 1 over x plus y is equal to x plus 14, right? So you can write x plus 14 down, and that's equal to 1 over 24. So now we just have a one variable equation. So this is easy. Now you can make the common denominator. So x plus 14 over x times x plus 14 is equal to x over x times x plus 14. That's equal to 1 over 24. So that means that not plus here. It should be a plus, not equals. So 2x plus 14 is like divided by x times x plus 14 is equal to 1 over 24. We don't want fractions, as fractions are bad. So we can do cross multiplication. So 24 times 2x plus 14 is equal to 1 times x plus 14. So 4x, so 24 times, not 4x, sorry. So 24 times 2x is 48x. And 24 times 14 will be equal to 336. 1 you can cancel, that doesn't affect the product. X times x plus 14 is x squared plus 14x. Now I can move like everything to one side. So to get the quadratic, x squared minus 34x minus 336 is equal to 0. Now you can factor to get that x is equal to 42. So 0 is equal to x minus 42 times x plus 8, right? X cannot be negative 8, right? Because you can't take like a negative amount of time to build something, right? So x is equal to 42. So that means y is equal to x plus 14, which is 56. And the question asks for how much time it takes for the smaller ant to build the anthill, so that's just y, so which is 56. So 56 is the answer. Now we can continue by problem 24, the hardest problem of this contest. We can write the solution down here. So to start this problem, like you want a quartic like polynomial that has like that has roots that you know. Then you can basically just determine what the polynomial is. So something else to notice is that f of 1 is 59, f of 2 is 118, which is 59 times 2. Then f of 3 is 59 times 3, right? So what you can do, you can let g of x be f of x minus 59x. Then g of 1 is equal to f of 1, which is 59 minus 59, which is 0. Similarly, for g of 2, it's also equal to 0, and g of 3 is equal to 0. So f of x is a monic quartic, right? So that means g of x is also a monic quartic. So it's equal to x to the power 4 plus something. And that's so that means g of x must equal to like x minus 1 times x minus 3. Well, sorry, x minus 2 times x minus 3 times x minus like some like the fourth root is unknown. So we can just like let it to be k, which is like anything. And you multiply all of that by 1 as it is monic. And so it's okay for us to not write that 1 down because 1 doesn't change anything to the product. So now we have determined g of x, right? The problem asks for what is equal to what is f of 9 plus f of negative 5. So notice, if you know what g of 9 is, then you know what f of 9 is. If you know what g of negative 5 is, then you know what f of negative 5 is. So if you know what g of 9 plus g of negative 5 is, then you know what f of 9 plus f of negative 5 is too. So our goal is to find g of 9 plus g of negative 5. And you can basically just plug it into that equation. So it's equal to g of 9 is equal to 8 times 7 times 6 times 9 minus k. And g of negative 5 is equal to negative 8 times negative 7 times negative 6 times negative 5 minus k. So this is equal to 6 times 7 times 8 times 9 minus 6 times 7 times 8 k. And this is equal to negative 5 times negative 6 times negative 7 times negative 8 plus negative 8 times negative 7 times negative 6 times negative k. And this is equal to 5 times 6 plus times 7 times 8. Because each of them has 4 negatives, so the negative signs cancel out, plus 6 times 7 times 8k. So that means their sum, g of 9 plus g of negative 5, is equal to 5 times 6 times 7 times 8 plus 6 times 7 times 8k plus 6 times 7 times 8 times 9 minus 6 times 7 times 8k. And notice the 6 times 7 times 8k cancels out, right? Therefore, the sum is just equal to 5 times 6 times 7 times 8 plus 6 times 7 times 8 times 9. And here is where you take advantage of the fact that Fermat Contest allows you to use calculators. You can find that it's equal to 4,704. So notice that like f of 9 minus 59 times 9 is equal to g of 9, right? Because that's in our definition of what g of x is. G of x is f of x minus 59x. So g of 9 is f of 9 minus 59 times 9. Also, similarly, f of negative 5 is equal to, well, f of negative 5 minus 59 times negative 5 is equal to g of negative 5. So now we can add both of them. So g of 9 plus g of negative 5, which is equal to 4,704, is equal to f of 9 plus f of negative 5 minus 59 times 9 plus 59 times 5. So f of 9 plus f of minus 5 is equal to 4,704 plus 59 times 9 minus 59 times 5, because we just moved this to the other side. And that's equal to 4,940. And the question asks, what is the sum of the digits of that number? So the answer is 4 plus 9 plus 4, which is 17. So now we are left with problem 25. And we have this kind of like sequence, and how many of A1 until A2025 squared is divisible by 2025. Again, note that it's equal to 45 squared. If a number squared is divisible by 45 squared, that means that that number is divisible by 45. That's equivalent to that number being divisible by 45, right? So basically what this question is asking is so how many of these integers are divisible by 45, which is equal to 5 times 9, right? So it's basically just asking how many of these integers are divisible by both 5 and 9. And we can solve problem 25 over here. So A1 is 1. A2 is equal to 3. And AN is equal to AN minus 2 minus AN minus 1. So, like, if it's divisible by 45, we can split it into 2 primes, which is 5 and 3 squared, right? So it must be divisible by 5 and 9. And we can look at each of them separately, right? So we can first start by like mod 5. A1 mod 5 is 1. A2 mod 5 is 3. A3 mod 5 So now we can like make a list, right? So A2 mod 5 is 3. A3 mod 5 is 1 minus 3, which is a negative 2, which is 3. And then A4 mod 5 is 0. And then it's 3 minus 0, which is 0. And then it's 0 minus 3, which is like negative 3, which is 2. And then it's 3 minus 2, which is 1. 1, and then 0. Now you can continue like listing it out, right? It's not that it doesn't take too long to like list all of them out, and eventually you'll get like repeats, because there are only like so many like possible like pairs of 2 consecutive like numbers mod 5, right? That eventually you'll just get a repeat. And like notice that listing all of them doesn't take that long, right? And there's not really another solution that's like faster, so we can just like list all of them. Well, there is another solution that's faster, but it's like more complicated, right? But like we want to let's keep it simple. It doesn't take too long to like continue doing it like this. And then I'll just give you the entire I'll just give you the entire list. And then 0, 1, and then 4, and then it's 2, and then 2, and then 0, and then 2, and then 3, and then 4, and then 4, 0, and then it's 4, and then it's 1, 3, 3, 0. So notice now we have found a repeat, right? It's 3, 3, and 3, 3. So it repeats. So because this sequence only depends on the last two terms, and we have found two terms that are like the exact same, the sequence will just continue repeating, and it's going to repeat with a period of 20. And from this, you can see that all n that are congruent to 4 mod 5 have an divisible by 5. This just means it's divisible by. Now we can do the same for an mod 9. And then you can do the same thing, right? I won't like write it out because you're basically just doing it all over again, but now it's for mod 9 instead of mod 5. And then you can notice that the sequence repeats with a period of 24. So now you only have to write for this one, you only have to write 24 like cases. Like, notice that like for mod 5, you don't have to write that less, right? And like realistically on the contest, doing that would take like 3 minutes. And doing mod 9 might take like 3 minutes again. So you can basically solve the problem in 6 minutes, right? That is a really good time to solve problem 25, given that the contest is 60 minutes long, and that you would have like, based on like when we finish recording the last like part of like questions 1 to 20, you'd have like 25 minutes left. That's a really good time, right? So this solution works. There are better solutions, but they might take even more time to notice and to like find out. Like this solution, I admit that it's like bashy, but it's like, it might just be like your best bet. Like it's like it takes a safe amount of time. So yeah, notice that so now you can notice that it repeats mod 4 and then you will notice that all n congruent to 10 mod 12 have an divisible by 9. So now just n satisfies both 4 mod 5 and n satisfies 10 mod 12. Now it's like a template Chinese remainder theorem, right? So that means the solution for n is you can like check 10 mod 12 and then add 12 until you find that n congruent to 34 mod 60 is the only solution. Right? So the answers, like the possible solutions for n is like 34 plus 60, and so on. And it stops at 2025. So you stop at n equals 34 plus 33 times 60, which is equal to 2014, right? If you add 60 to that again, that's more than 2025. So in total, there are 34 solutions. There are 34 possible values of n. Because this is 34 plus 60 times 0 until 34 plus 60 times 33. So like 0, 1 until 33, that's 34 solutions. So the answer is 34. So now we have solved all of the final 5 problems of Fermat 2025. And with the first part of the video, we have solved the entirety of 2025 Fermat Contest. And notice that this took around 25 minutes, right? So if you combine with that, it took like 35 minutes to solve all the first 20 problems. That's like 60 minutes for the entire contest, right? So this is like, so if you did this on a real contest, you would have gotten perfect score, like assuming that you didn't like make any like mistakes. So yeah, now we have finished solving 2025 Fermat Contest. Thank you for coming to this video. Thank you for listening. Have a good day.